Today's lecturer is Nazaroglu from the University of Cologne, and Chania is going to talk about Rademacher expansions for force and modular points.
All right, thank you so much. And let me start by thanking the organizers for this wonderful program. Today we're going to switch gears to number theory. So let me perhaps start with what we're trying to accomplish. Very general. Suppose you have a sequence of numbers indexed by integers plus non-negative integers. A very general philosophy that goes back to a very mathematically used by earlier. Whenever you have something like this, so you start having to find a generator. And then hopefully this thing is convergent in some region at least, and perhaps you can get more information out of the generating function. Perhaps some differentiability properties, perhaps some difference equation it satisfies, and using those you can obtain information about n. After the advent of complex analysis, of course, you can do much more. You can extract the Fourier coefficients with contour integration for any contour that surrounds the origin and is within the radius of convergence. You can form the integral over here and try to study an by studying this integral. Now, one thing you can do, of course, this is a holomorphic function, so you can deform the contour. And the idea here is to deform the contour in a way to sample the most dominant parts of f of z. This is, of course, a crucial tool in analytic number theory, going under the main circle method. And many of its developers are actually around here. So that goes back to Hardy, Ramanujan, and many other developments by Littlebrook, Davenport, Navarro, that's it. Many. For example, as a problem you can study with this method. Suppose you'd like to work out, study ternary Goldbach problem, sometimes also called the weak Goldbach problem. It said that any integer greater than or equal to 5 can be written as sum of 3 primes. Well, one way you can approach this problem is to start with the function Sn of x. You can sum over all the primes less than or equal to n. You can form this sum, and then compute the function integral from 0 to 1 Sn of x cubed e to the minus 2.5 n. So this gives you a number of ways to write n as sum of 3 primes less than or equal to n. Okay, but obviously, the problem you'd like to study is not the number of them. This is a much harder problem actually than what you'd like to do. The problem is just to show that there exists a way to represent them as 3 primes, and that leads to many variations indeed, many technical variations in the method. So, since, as I said, you don't really care about the total number of them, you only care about the existence, you can modify the coefficients in Fn. You can control the contour, obviously. Perhaps parametrically in some parameter, and you can control those parameters. For the contour and whatever else that you may want to insert.
I think it's common with them to go for problem.
So the problem is saying that, yeah,
Sorry, maybe if we first time I think it's another stated. Is there any odd instances?
greater than or equal to 5 can be written as sum of 3 prime numbers. Still, that's also fine. Can be is the exactly right. The more famous Goldbach conjecture is saying that even integers can be written as sums of 2 primes, but this is a weaker version. Going into that, yes. So let me mention that. Already in 1937, Ramanujan, using such analytic number theoretical methods, showed that this statement holds for all sufficiently large n. That's great news. So if it holds for sufficiently large n, you can check whether it holds for smaller numbers, and if it holds, then the statement is okay for all numbers. But shortly after Ramanujan's work, student actually computed like what the bound is for that sufficiently large statement called, and that's around n to the 4 million. So certainly not enough number you can check below that. So yeah, a lot of effort has been spent on improving on these, and actually a proof that completes the proof of the conjecture only came about a decade ago in 2012, 2013, in a series of papers. Half-Life managed to bring down these numbers to something manageable by computers. And now we have a proof for ternary Goldbach conjecture.
Or you check up to some number and then.
Yeah, still fairly large numbers, but so it's very technical work in both fronts, both in technical front to bring down the number and on the computational front to get as many numbers as you can check.
So why would you know
Which part? Like I'm cutting it off because I'm worried about convergence. And Sn itself, as I said, is not that important because I care about existence. Therefore, perhaps I can insert coefficients over here. As long as I can check the result of this integral with some coefficients is non-zero, still I have a proof for the statement for that particular number. That's like. Any other questions at this point?
So did we know the method?
Yeah, well, this method, like n variations of that. Analytics, a large portion of analytic number theory is refining techniques like this.
Yeah, I did.
All right, so
Sorry, perhaps tangential, but I'm very ignorant. Can you comment a little bit on what is the relevance of this conjecture being proved? I mean, is there any application?
application probably not.
Okay. I was wondering whether there was any.
Long-standing, like the original Goldbach problem itself is a long-standing conjecture. That's part of the reason people care about it. The interesting thing about ternary Goldbach conjecture, it's a bigger version that we can't,
But does it have any implications further in number theory? Like, does it have any utility?
The problem is not problem out. what's more relevant is the methods, like methods used here can be applied to other numbers. So well, that's that.
And very naively, the large n, could I think about it? I mean, for numeric or a completely different story, but some sort of parallel approximation.
Yeah.
More.
Yeah. All right, so let's move on to what's it like to talk today about. And well, for us today, the f of z will not be any function, but it will have some sort of modular properties. So these will provide us a large set of symmetries. And in turn, that leads to strong constraints on the coefficients. Yeah. The perhaps the most well-known example of this actually goes back to the origins of the circle method, is the Ramanujan, and that's for deeply holomorphic modular forms of non-positive weight. I will not be repeating that as something to thought. I'll always consider non-positive weight. So starting with Hardy, Ramanujan. A lot of work contributed by Rademacher. And of course, many others afterwards that work on variations of it. The original problem Hardy and Ramanujan looked at was computing the integer collection function. And the generating function for this is well known to be a modular form given by the Dedekind data function eta. So what it's a modular form of weight minus a half. So first thing you can do, of course, is to study the asymptotics of Pn. And there you obtain the results for n3. So this is, of course, a saddle point like approximation, and it can be obtained with modular transformations and also in other ways too. This is, of course, in the literature also what's called the Cardi formula. With modularity and holomorphicity, right? You can go much further, and that is the topic of today. You can not only get the asymptotic expansion, you can do it to all orders, and you can also package it inside formulas that are not only asymptotic formulas, but convergent formulas. For Pn, it looks like the following. But there are some constants. The constants themselves are not too important, but right anyway. And an infinite sum involving what is called a Kusterman sum. This is a finite sum that packages the phases that arise in modular transformations. And then an I-Bessel function. I3 halves I over K. Oh, it's not visible there. Perhaps I can shift it a little bit.
We cannot move the blank.
But let me write it down below. I3 halves 4 pi over K. Sine squared 1/74. Okay. There are two features I'd like to point out in this formula because they're going to come up again and again. The degree over here is not arbitrary. 3 halves is 1 minus a half, and minus a half was the weight of the modular form, of the involved modular form. The 1/24 over here is also not arbitrary. 1 over eta now has a Fourier development of the following form. That starts with q to the minus 1/24, and then goes on to the higher orders. Everything is exponentially suppressed as tau goes by infinity, but this one gives a exponentially growing contribution. So this 1/24 is the coefficient of that exponentially growing term. Exponentially growing term, and minus 1/24 is the coefficient we're trying to extract. From sorry, yes, of course, 1 to infinity, not the 1. Yes.
So you make a whole when you mentioned it about judgment of what I'm following. What did you really evaluate this formula? Or
This is valid for any n. Valid for any positive n.
Right.
You can insert it as a convergent expression. With respect to n, rate of convergence changes a little bit, but it's convergent. No. Well, we're gonna go for more complicated versions of this stuff.
you say that so positive. I mean, this the binary code conjecture. You are done.
Yes, that's
Okay, and then you start.
yes. We're starting with the modular ones. Yes. The point is, these kinds of problems are much harder because you don't have the analog of modular.
This plot was just coefficient and put.
Yeah, this one, right? Yeah.
Can I also question? Yeah, you said that you want to completely formulate the model points instead of non-positive mode.
Yes.
Inside negative.
I said non-positive. It works at weight zeros with much harder work. There you have, for example, if you use the trivial bounds on the closed term and sums, you're restricted. Well, the proof goes through for negative weights, but you can improve bounds on closed term and sums with better technology, and that leads you to weight zero as well. This gets especially complicated when you have weight zero and false guys because you have generalized closed term and sums there, but still doable. Or there are examples that are done. These are Bessel functions, but okay, in the context of Pn, these are actually, well, like any Bessel function with half integer index, these are elements. This is an elementary function. So I can write it down. I 3/2 and well, since I 3/2 is going to appear later on, it's right there. It's the it's given in terms of coefficients.
Out of curiosity, are there similar results for application functions of integers with constraints?
Yes, that's there are there are very many variations of that, and sometimes like mockness or falseness and etc. also start to come in, like when you start inserting constraints into your partition. All right. So this is the classic. This is what classic holds. What we'd like to go further is a sorting that's within the last decade. So we'll be looking for now Fourier coefficients of, for example, not modular forms, which themselves are not modular, but they're non-modularity is controllable enough in a sense that these techniques will have a chance to work for them as well. Let me mention a few words along these directions. Or I don't know, I will say next, but I won't repeat that word too much. Modular forms. And yeah, for later reference to this depth one case. The first examples that the technique was first started was first developed in 2009 paper. Doing what I'm over. And they were studying another combinatorial problem. So partitions without sequences. By which I mean you have any integer partition, but you don't allow consecutive numbers to be counted. So there is the generating function is found to be a modular form, mixed modular form. Later on, I will tell you what modular is in a second, but let me mention the existing work for now.
And so basically the problem is that the eta has a pole, that's why the problem.
Yeah.
And but can you tell us under which condition this whole thing goes through?
I will. I will mention like what parts of Eric modular contributes to these things. We'll see. Modular 2010, shortly thereafter, actually applied this to compute an exact formula for U2 local vitamin invariant from C0. Another word worth mentioning is Fourier waves. 2017, where they applied the same technology to whatever for get black hole counting. In an equal force string theory. So they applied it to mock-Jacobi forms that arise from the work of double Murphy and Laguier, and there are much more recent development along this front, but the authors are here, so we should ask them. So, the more recent thing is in the two modular forms. I'll say what these are. But let me mention where they appear. In general, higher depth, modular form appear in, for example, even if you compute even higher range, also the same invariance on CP2 or similar surfaces, you get those. In black hole counting, in equal two string, type of LPR, you start to get these. And more brow application is to non-compact CFPs. So, for example, you can compute elliptic genera using for GLSMs with squat choice manifolds. And those are also can be defined as modular. That generalizes the usual story about the cigar CFP having a modular partition elliptic G partition function, and then the version that is trying to define that modular. That one also does. Like that one is the usual modular case. Then you have higher depth cases. I'll tell you what that means soon.
Okay, yeah.
Okay, and Rademacher expansion is also done in this case. Next one was with Newman, and that was for the three local engineering from CP2.
So it's one is one, it's two.
Yeah.
And then the right goes. I mean that goes.
Yes. Yeah. And the final variation I will mention is for both modular form. So started this here in there's a valve for so-called happy variants. And also they appear as characters in long BLH. Certain no algebra that actually as characters. The Rademacher expansion for that is again now. And this is a combinatorial way approach. So model sequences, which I'll mention a little bit. And there are many follow-up works now that can actually use the results of such Rademacher expansions to study to prove identities satisfied by whatever number you're computing. For example, there are conjectures that say some of these Fourier coefficients satisfies the so-called log concatenative property. You can use these expansions to effectively study their asymptotics and prove that property for large enough n in a similar way, and for small enough n, you check for the others. You check. Absolutely, all right. Any questions? Because I'm going to move on to more expected science. Let me go for that story for example. Not example general story. And let me consider for that the YouTube of this. So this is the content of the Ramanujan paper I mentioned earlier. In this context, the modularity is a result constant of S duality. We're studying a topological system, of course, we're not on CD2. And checking modularity was one of the quantitative checks. Well, but one of the things they yes, the modular that it's modular probably is from the exact. So let me mention what the function is actually. So the partition functions here are generating functions of the earlier numbers on the corresponding stuff on moduli spaces, and the earlier numbers there were computed in math literature earlier, Yoshioka and Yachiko computations, and the result given as where the data function is something we already encountered. A alpha tau is 0 to infinity, 8 or n plus 3. The coefficients over here are the so-called Fourier numbers. So you can take any quadratic form with integer coefficients like ax squared bxy plus cy squared, right? And then you can act with SL to Z on the xy pair. That induces an action on the coefficients of A, B, and C. So you have an SL to Z action on quadratic forms. Then you can start asking the number of equivalence classes under for each discriminant. So these are for negative discriminants. They are weighted by the holomorphism groups that remain for each equivalence class. So these are going to be rational numbers in particular. Well, there's a 0th one that's set by modular properties, minus 1 over 12, plus 1 half q, plus 2 squared, goes on for the 0th component. Okay, those are the three expansions, the leading terms of this. It is. It is, because, well, it's actually a pure modular form. Well, I'm gonna tell what it is. So let me say, let me mention its modular property first. That we already heard. Well, already where count finds going to be A in some of these. So H alpha tau is a modular form. What does that mean? So it means two things. We see the holomorphic part of a real analytic modular form. So it arrives at the boundary value as we take tau bar to minus I infinity. There's a function a hat, u is denoted by position is denoted by h hat. This is the function, and h hat itself is modular. So let me write down the modular property hat. So any S alpha D, H alpha for vector value of modular form. I'm dropping tau bar from the equation there. It's transformed like a base 3 times modular form. Alpha is an index, 0 and 1. It takes two values, 0 and 1. Yes, yeah. So the discriminant is discriminant of a quadratic form is b squared minus 4ac, right? Modulo 4 it can be 0 or 1. These are what they're distinguishing. H0 is counting ones with discriminant modulo 0 mod 4, discriminant equals 0 mod 4, and the other equals 3. Well, equals. Yes, that's how this is. This is the dual Y representation to the lattice A1. Or put it another way, you can be without the Y representation for the lattice E7 by the usual decomposition of EA2, E7, and A1. I don't know actually. I don't think it's one of the mock. No, it's I don't think it's listed as one of the mock data. I'm not sure. To be honest. Sorry, which some? Yeah. So this is a two components vector object. Under SL2Z, the two components are mixed. This is the only thing I'm. No, just yeah. Yes, yeah, or you can combine it into a modular form in Cologne plus space, but I find this language simpler because you're using this full SL2Z to quantify it. And that's one property. It's part of the holomorphic part of a real analytic form. But that real analytic modular form is not any real analytic modular form. It's now bar derivative satisfy the following property. It is given in terms of ordinary modular forms. Where I define the theta functions as follows. So these are theta functions for the one-dimensional flat. It's gram matrix 2M. And these are known to be modular, vector valued modular forms. Classically from Jacob's work. Well, we are only looking for the theta one, the alpha component of here is corresponding to the alpha component of H alpha. For us, n is one. For this guy, n is one. If I can get to the depth two one, then there will see theta three as well. That came from the book of Witten and Marion, but from the for us, yes, it made it negative weight. It created the exponentially growing parts, and so it allowed the application. No, it could. So per our race paper, actually, one of the cases reduces to applying this for a to the power.
But the H is the important part here.
Yes. Yeah, for minus eta doesn't matter. Well, it is what I meant by being a mixed modular form. If you compute the tau bar derivative with eta around, that eta would also appear by that side dotted modification. So now you have the modular form of minus tau bar and the modular form of tau mixed together in the tau bar derivative. That's why it's called the modular form. Yes, absolutely. Thank you. There should be one. All right, so the tau bar derivative and the fact that as tau bar goes like minus infinity, that you should get H alpha gives you another way to write down H hat, which is beautiful. So H alpha tau, the boundary value, and you add an integral from minus tau bar to I infinity. So then tau bar goes to minus I infinity, that explicitly goes to 0, and you just plug in the derivative you see over there. So this is the total integral. If you want to be more specific, you will call it a holomorphic integral. And the good thing about it is that it also makes manifest many of the modular properties. The integrand is modular covariant. It's the simultaneous W and tau. The problem then reduces to the modular transformations of infinity. Infinity is not left in there, another modular transformation. So there's a leftover piece if you perform modular transformations. And this is where we are heading. All right. So let me first perhaps write down the question I'd like to answer. So we have F alpha, obtained by dividing by eta 6. If you look at the three expansions of those, you have the term here delta alpha 0 to the minus 1/4. This is the only exponentially growing part as tau goes by infinity. Then you have exponentially suppressed. And it goes down to infinity. Let me put the coefficient P alpha and all right, so our goal is to compute the alpha ends using Rademacher. So the starting point is easy, of course. We're just going to write down the alpha n as an integral from I to I plus 1. The point I is not important in a point on the field, of course. This is the integrand is periodic. 2 pi I. So the right-hand side of this equation is what we got to study. Now, SL2Z, remember, well, acts like eta of p plus b over sigma of p. So it relates infinity to rationals. So the exponentially growing behavior near the infinity here would be cast into exponentially growing behaviors near the rationals now. So we're going to take a contour that gets closer to the real line. That's going to sample these strong growth points around the rationals. And those will show that those will dominate against the rest. So that will lead us to the Rademacher. Well, at least without the error to modulator, that would be the full extent of it. The term over here with negative exponents, well, we call the polar term. Determines together with the self-complete transformation, determines how the function grows near the other.
When you're always focusing on.
No, because the SLP is mixing different components. So at different rationals, you'll have mixtures of. Yeah.
But you could have started with mixing.
Yeah,
Basically, but eta.
it's not relevant. Well, yes, no. In that case, it's not relevant. It's all still, well, it, whenever I wouldn't even be dealing with the non-plus and Vegas. But I'd like to focus on the Mach monster.
So that how that H hat that is not, that has good properties for H.
Yeah.
Both.
Prime, H times H prime equals 1 modulo K over 2. And then you just complete it with the final. Which one? Oh, behavior. Sorry, that was. Good. So let us start. Irrational. I'd like to probe around. The K squared over here is just for convenience, so the Z will be the factor that goes to the line. I'm getting close to the K point. This value is my these are the multipliers corresponding to A times K. So these are the factors I star that transform the H alphas plus the phase factors that appear in the transformation of A dot. Let me package all of that inside this side. And then I go back to my original function. Q alpha H prime over K plus I over Z. Now, if this were a ordinary modular form, I would be done, and that would be great. As V goes to 0, this goes to infinity, and I know the behavior of my function at infinity. But I have more. Vi over form. This function f of tau is the 1 over eta tau to the power 6 that I inserted that goes along with the H alpha. And what I'll denote by epsilon in error term. Okay, so the main difference in my modularity is this error term. And this is a period integral. Basically, what we had in the Einstein integral, but the lower bound now goes to a rational number, rho. And since you decouple the lower bound from the point tau, this has much better relativity property. It can continue to the lower half plane as well. Same thing, theta 1 alpha W. Now, as I said, our interest is in determining what part of the right-hand side grows exponentially as we go. That's what easy to do for this term, but what about this? From this, we have a q to the minus 1 over 4 term as well. That certainly provides an exponentially growing contribution. But what about the epsilon? The tau dependence is inside this denominator, so it's not at all obvious like how it behaves as v goes to 0. All right, that's our next test. To recast the error to modularity in some way where we can see the growing behavior much more cleanly.
H prime equals 0. Or
Oh, yes, yeah. If the most dominant term is given by the behavior around 0, yes.
and then the error part important.
Now, so usually if you have like in the generic case, the zero component is the most dominant one. The others are exponentially subject. But there are situations where the growing parts and the vector value transformation are so transparent that the zero component has a lower growth. The S transformation, the behavior near 0 is not and may be subleading to the others just by accident. Yeah, because of passage.
So the error part can be.
So those other rational points, H over K, can be important. Well, we will do the following. We will perform the S transformation, and look at look at the free expansion. So it can be that the leading polar term may be canceling for the expansion around 0.
You can't just break it as the same as what happens when you take the word how far.
Sorry, what's the relationship of our derivative?
So when you look at, because it's basically what the shadow is doing.
Mhm.
Right?
the epsilon term is. But the comment about the Carter formula also relates to if you only had a holomorphic modular form as well. The polar term can be canceling for the behavior near zero for some reason, as I said.
It's vector value.
Yeah, vector values.
No, that's okay. No, I just meant like the Mach part.
I see.
That's the thing that I'm. Like when is the Mach part and going to like maybe washed away?
Oh,
Or would generically if it's zero then. No.
it's not zero. Well, that's part of the point. It's non-zero and it's gonna give contributions. And for example, in this case, both f of alpha and this guy over here has the q to the minus 1 or term. So the leading exponential behavior is the same. And actually, if you compute the Rademacher expansions, both the holomorphic contribution and the Mach contribution will have the same leading exponential contribution.
Okay.
But the Mach term would be power suppressed compared to the other. Yeah.
Oh,
Power suppressed, yes, in N. Okay. I will see the reason. All right, so our next step is beside this, error to modularity. We're going to recast this in terms of what's called a Mordell type integral. Where the graph behavior would be much easier to see. So what is that? Let me just insert the, I have a theta function inside, so let me just insert its definition there. So the error to modularity that I care about. Let me invert C. So instead of V going to zero, I'll be caring about V going to infinity. At least we know it. So there's an infinite sum, that's the lattice sum of the theta function. There are phase factors that come from the terms inside the theta function. And then I have the integral. So I have commuted the sum with the integral that for certain examples that require some care, but it's not. And one thing I can mention, for example, is that this integral can be expressed in terms of complementary error function. I will not give the explicit expression with the formula, but this is the familiar factors of error functions if you ever work with Mach modular forms. And another point is that this thing behaves like lower m squared as m goes to infinity. That's why it's converging new things through that. All right, so good. We just rewritten what we have, but now we have an identity. So you have error functions. Error function has, of course, many different ways that you can write it with. And one of them, particularly useful here, this holds for any real, any complex needed real part concept. And this is the key result here because the right-hand side is precisely what's going to come in this formula. So we're going to use it with s equals to m/2. And commute the m sum back inside the integral. It requires a little bit. Not too hard. constant factor, not terribly important. Then there's a finite sum. That takes care of the things here. Here's the point. You have an integral over all the real. And we have a kernel that's given in terms of the cotangent of I W plus R over 2K. Back up W over here. 2 I W squared over 4. All right. You can simplify this a little bit and rewrite the fact over here in terms of sinh and cosh functions of W. Complicated kernel, but here's the important point. Inside the integral, we have e to the minus 2 pi b times something positive integrated over, right? Now, this was the error to modularity. We also had this factor of f over here, which had this q to the minus 1 over 4, which had a growing contribution like e to the 2 pi b 1 over 4. Right? This is from F. And these are the only V dependencies inside this expression. Now you clearly see which parts are exponentially growing. The combined object, 1 over 4 minus so the exponentially growing parts are from 1 over 4 minus W squared over 4. So there's a finite region of W now that gives rise to a continuum of polar terms due to their modularity now. That's the main difference. Mach modularity instead of discrete polar terms gives rise to a continuum of polar terms. How does it look? Well, the same thing. If you multiply with this factor, you're just going to cut off this integral at the points 1 plus minus 1. No. Everything is exact so far. And actually, I'll later debate this out. Oh yes, well, sure. Well, lots of prefactors for this.
Just completing the squares and then.
Oh yeah, that part is yes. I mean, that's the V dependence is contained to this Gaussian term. Yeah, that's the crucial point. Yes. So let me not go through technical details from now on, but mention the following. So now you can repeat all the things people do with Rademacher expansions of holomorphic modular form, but with this continuum over terms. You show that the remaining continuum nonpolar part as well as the discrete nonpolar parts do not contribute if n goes to infinity. N was bounding the denominator of the rationals we are considering. You can use Rademacher's contour. That's also not important. That's the choice, but it's a pretty convenient choice. You can do all those things and obtain an exact formula. Let me schematically show how it looks like. So there are constants and powers that I will not be writing. Who's going to come against it? I will not writing. Just want to point the following out. There's an I-vector function, I pi over 2, 4 pi over k, square root of alpha. That's one term. Then another one. Third includes some sounds again. Not important. then an integral. And here you have a kernel function. That's basically this function times factors that are going to come out of the Bessel function integral that shows up in the Rademacher from 4. And integrate it against what you would get from this continuum of 4 terms. One over 4, 1 minus u squared. These are the contributions of the polar terms, and the Fourier coefficient that you like to get. So it gives rise to an expression of it.
I got a little bit lost.
So let me tie it back to what we had for the integer partition function. There we also have the isotope functions coming up. There are factors that encapsulated the phase factors that appear in the modular function. Those are still there in some form or another. There are various powers of an alpha that come from the integral factor. Those are also there. We can recognize 2 things. So we have h alpha over eta to the power 6, right? So this has weight minus 3/2. 5 over 2 comes precisely from that, 1 minus 3/2. Or pi over k is always there, but then you have the 1 over 4 factor that's coming from the polar part, in fact, the holomorphic part. And alpha is what we are trying to extract. And same thing over here. I5 over 2 is still there. The only replacement is because we now have a continuum of polar terms extracting from 0 to 1 over 4.
Yes, but I think it's like I just lost you in the error.
Because the V dependence, so the V dependence is constrained to these exponentials now, right? So now you're integrating over a range of coefficients given by W squared over 4.
But then what is hard to how to define you.
Oh,
What
It's-
you and
probably the same thing actually. So because the limits learn W between W plus 1. Sorry, yes. I wasn't sure whether maybe I was thinking maybe I rescaled it.
But it's integrated. Or if it's not integrated.
It is integrated over.
you don't.
But it's or either. So the you can go.
Yes, hard to do.
Sorry, yes. Yeah, so that's the general form you obtain. Maybe a small comment if you're familiar with the literature over here. The way we've written the arithmetic is not unique. You can perform integration by parts perhaps and change the kernel a little bit, and you'll start to get powers of V in front. And in those versions, the error to modularity will be contributing the Bessel functions that have a different degree. You may see that in papers, but it's just a choice. But I find this version.
What is KW?
KW is this thing, this function times there's a power of 1 minus W squared that comes from the Bessel function. I didn't want to write down.
So it's like
Oh, the Klusterman sum is still here, but it's a finite sum.
like a version.
Yeah, but, well, then maybe I should make the following distinction. The Klusterman sum, there's a generalized version of it, but still a discrete sum that's appearing outside.
I know, but it's
Maybe. Can be thought. Yeah, I guess. I wouldn't object too much. Sure. All right. Any questions so far?
So the logic is formalized. The dots, they say something that's not important. But
That well,
always polynomial.
there are polynomial terms inside that they have.
So it's
But the exponential term extract from the data. And the reason the Mach term is general source of that is because of the integration. to do a cutoff. Now, we're gonna see that the Gaussian, the integration produces powers of analysis compared to this.
But this part that you're writing up, and it's a little bit to understand it carefully, like, if I did it for a different, modular form, would this be just something that is clearly controlled by the symmetries of the initial modular form that you have?
Symmetry and the shadow, but you can understand the
Yeah.
shadow as the boundary behavior of
Right, but it's
the
not,
zero. Yeah.
not controlled by, like, for instance, what things that you're emitting here, like, for instance, in the Rademacher expansion, you have specified the coefficients of the polar space, and then.
Oh, yes, okay.
That's form.
That's another problem there,
Right.
yes.
But then, like, the Boosterman sum, the Bessel function, that's all universal, that
Yes.
is always there for, like, no matter what you do. So is this part, I just want to appreciate.
This is the universal part, in that, yes, yes.
So,
Then you may ask, like, where these four terms are coming from. That's also.
yeah, but that integral that you highlighted there is not something that it will be very, like, if I just tell you which type of modular format, then you will. have
Yeah,
that,
yeah.
Regardless of what.
And like I said, the form of the idealism function is pretty universal. It just follows from the weights and whatnot. The kernel follows from the shell.
Right.
There you require a theta function.
Transformation properties that you have, and like,
Mhm.
not like, for any, what was this, that one?
That was that one, yes. Yes. Yeah, with the flag. Good. Okay, let me make that comment right away. Well, okay. Well. If you have that two modular form, let me give you an example. And that can be the three of it and then that's a very basic step to modular form, very nice. So this guy has a modular completion, which is a real analytic modular form. It has some holomorphic part. That gives the probability, but the error modular is the Einstein integral, inside integral now, you don't only have a modular form, but you have the completion of a lower decimal form. In this case, actually, this is precisely the completion of the modular form you've seen earlier, because it's plus numbers for the number. Then you have another network. Yeah. You free population is just this guy divided by the. Right, so that's the completion. So Talbar derivative, as you see, gives rise to both the completion of a lower decimal point. This is a three-step modular form. And nine. This has base minus 3.5, just like what we looked at earlier. So you play the same game. You probe the behavior near the rational H over K. Modular transformations tell you that this has the following form. The multipliers active inside this pi factor. The contribution of the holomorphic part. which will be what we were to limit the bit stuff for the modular form. Then two terms now. One term that comes from the holomorphic part of alpha. And two-dimensional area modularity, just like we've seen earlier. And the next part is the contribution of the shadow of this together with the mu from the contribution or the depth of the. As before, you have the holomorphic, the holomorphic modular form 1 over eta to the power 9, the eta power in front of that accompanies it, and you have a area modularity. That's given in terms of the iterated integral now. Just schematically, let me show how x1 looks like. So rational to I infinity, the first integral that involves theta 1 alphas. Let me not write down the components. And another integral inside dw2 going from w1 to infinity. So theta is. Okay, so that's how the Ertz modulator looks like for the depth 2 modular form.
That's good. So you divide by eta.
Yeah. It creates the pole and it's well, it makes the weight negative. That's the essential point. The poles essentially come along, have to come along.
Boy, it has the same denominator. But you said this whole thing has to be, the element has to be modular covariant.
Yes.
And then you tell us what weights the two side. The one is probably 1/2 the other.
This as well. This, okay, now we have to distinguish two weights. We should be talking about weights in tau and weights in W. This guy has weight 3/2 in tau and weight 0 in W.
But W is
But W, there's still W independent, which just weight 0 in W. But yeah, it is important. That it depends on. This has weight 0 in tau and weight 1/2 in W. So the weight 1/2 in W is precisely why you see the 3 over.
That means you're only something like that.
How many?
Like that.
The definition of depth here means that the tau bar derivative, well, I define things with this. So depth 1 Mach modular form, the ordinary Mach modular form. If you act with the tau bar derivative, will give rise to a modular form minus tau bar times modular form in tau summed over. There can be many terms like this that are tau 2 bars. Good. What this thing does is replacing the m tau factors with something more general, with completions of lower depth Mach modular. So at depth 2, recursively now, the depth 2 Mach modular form will have the same structure, some modular form in tau bar again, but now the completion of If they, depth one, not one. At depth two, that would be replaced by depth two. So depth R is determined in terms of populations of depth R minus one.
You will also have a continuum of forwards.
Yeah, yeah. Yeah, the structure will be pretty similar. The isotope functions are pretty much the same, but the continuum now has the form of an two-dimensional integral. Good question. That's fine. Those questions are always good, I guess.
I was just curious, like, okay, so maybe for the previous example, you had like the DL cell, right?
Mhm.
So now I'm just interested in N being very, very big.
Can be or don't have to be.
No,
Like,
no, no, but
You-
living in some,
okay.
so what would you, so of course there's an exponential coming from the decimal.
Yes.
What would you write in front? Like what is the,
Well, you can compute the power factors in front. I, of course, don't remember that. Okay, but you can actually compute the full asymptotic expansion very systematic forward.
yeah, but I just want the version of like, I would still think.
Okay,
I just want that part, like that. So I'm just curious, like, what is the integral doing versus, like, if I was naive, like, and I would have just thought first. Yeah, yeah. Because it's basically, like, from here, I can just say, there's a way to get exponential growth. But it's coming
and you
from-
can see the coefficient of the exponential leading the exponential on the
Yeah,
same.
but I want to know what multiplying the exponent,
The
because that's where these guys come in important. The fact that you get e to the square root of n over 4 for the both sides.
yeah,
I didn't care, I didn't need to know that color part, right?
of course, the parts that I information become important over here, but they look pretty similar in many respects. I think that's also the case, but you two things. Okay, the explicit n powers that you see inside the expressions are pretty much the same. The integral now set up with a because further and also power suppressions compared to this. So the reason for the n power suppression is the integral, not the explicit factors in front. That was certainly the case for U3. I think it should also be the case for U2.
Way dependent. Yeah, I would say.
Well, sure.
What I guess one.
Okay.
But it hasn't been worked out, like, sort of like, if you give me
Any no, but on particular examples, yes. Actually, people. What is what?
no, it's like, for instance, for the, if you write, like, the Rademacher, like, you can very easily read off, like, no matter what the form is, you tell me what the weight of the form is, like, I will tell you a very large value of spend. Depends on what you say, yeah. What it's like the.
I see.
This is a universal formula that basically you just have two inputs of the form. And so I'm just curious, what is the analogous version of the modular case? Like, you know, in the very large n behavior, it is just controlled by.
Powers have easier universal behavior. It should be done by base and the n power suppressions you obtain the powers in there. That's also universal. Now the less universal part is the constants you also put in front of those. That depends on the kernel. So the best I can say there is, I guess, that the constants are determined by the shadow, but I don't know if it's like I don't think it's written anywhere like that because it is a universal formula. But given given the shadow. This is the-
But you.
Not in complete generality, but for classes of shadow. We can have different classes of shadow. If not, let me very briefly in the last 10 minutes mention the false counterparts of these. At least let me tell you what the false theta functions are and how their modulator looks like. How some of these setups are like those people. So for the false modular forms, the first example of the Rademacher expansion is in a combinatorial setting. So let me go to that combinatorial setting, quickly mention what this is. So this both in the context of so-called model sequences. So of certain size, the unimodel sequence is what? It's a sequence of positive integers. They run from 1 to s, let's say, where I require the coefficient, the numbers to be growing at first up to some so-called p, and they should be decaying back until the end. So this is the unimodel, and so this is in a way another restricted version of parts. And I call their sums their signs. Now, if I notify UN the number of unimodel sequences of size n, then its generating function is known to the class result. And it's given by the beautiful color in front, and then infinite sum over the partial. Well, let me rewrite it one alternative way to emphasize the modular components. There's one piece I will do. I'll tell you what sign is. Equals to L squared plus 2 to the 1 over theta squared. Well, 1 over eta squared is the modular piece, kind of that. Great. Psi tau is the full theta function. So you define it like the aspect of the theta function, except there's an extra insertion of sign factors inside. So without the sign factor, this will be the Jacobi theta function theta 1,1, but theta 1,1 would be wretched in there. So this sign ensures this thing is not. Good. So both theta functions can be discussed in a way very similar to indefinite theta functions, and a lot has been done in recent years. That is especially relevant for higher ranks. But if you only care about like unary theta functions, one-dimensional lattices, one-dimensional full theta functions, then there's a much easier way to see how these things fit into the modular RAM. And you can just apply one single lemma, which also one-dimensional fine lemma, which said that if you give me any real number L, then sine L times 2 to the 1/2 L squared is equal to the integral from tau to I'll write it as tau plus I infinity. For W. Okay, let's decipher what this thing means. So if you're performing sums over L, their left-hand side wants to combine into a unary pole theta function. So I can use it in something like this. The denominator over here, if you sum over L, wants to be combining into a base 3/2 unary theta function, ordinary one, so perfectly modular. And this integral is similar to what we've seen before. It's an Einstein integral, but it's the holomorphic counterpart. So the integrand is modular covariant. It's the boundary at I infinity that breaks the modular properties. But now you can tell what the modular to modular is. It's again like here, a period integral from a rational to I infinity of this modular covariant object. That's the to modularity for the post data. I've written I infinity, well, tau plus I infinity, because and obviously that I'll be using the principal value prescription for the square root of it. That called the branch cut in the W plane, starting from tau and going all the way to I infinity. By tau plus I infinity, I mean that I'd like to do the integrals from the right hand. So I'm picking the sheet, Riemann sheet that's relevant to the integral. That's a small complication in dealing with these objects, but it's not. No, well, you can. So from this picture, this is a very simple object, but you can view it also as a part of a bimodular form. Take that integral, cut it at a point W, omega, let's say, and transform omega and tau in the same way on our modular transformation. That's modular in them. Then you can obtain the same object by replacing sign factors with error functions, with appropriate error functions. That's the point. And the next point is in the higher rank versions of it, now you can use the technology of generalized error functions to study similar modular completion, so to speak, for the higher rank false data functions, which is a bit more because integral picture still holds at higher ranks. You start to get iterated holomorphic Eichler integrals, but the number of them grow quite fast with rank. If you're talking about rank n false data function, you need to be talking about n factorial of those iterated Eichler integrals, and their Fourier expansions will not have integer coefficients, unlike the false data function where integer coefficients are very natural. Yeah.
Was this example the one that gave us the notional false, or the notional false convert?
False data functions are really old. Actually, it goes the Jacobi data functions themselves goes to a book of Jacobi where he poses a probability question whose answer is the Jacobi data function. He actually poses two problems there. The other problem is a solution in terms of false data function. So the history is all the Jacobi data functions. Now I've run out of time, but let me mention that you can perform the Rademacher expansion for psi over eta squared as well, going through a similar story. What changes? Let me outline that. In the mod cases, the kernels were expressed in terms of Cauchy and sinh functions of W. Now you'll start having trigonometric functions. Moreover, the kernel will start having poles over the integration region. So those are extra subtleties related to false cases, but they also give rise to exact formulae.
So then the answer can form.
Very similar to yes. Yeah. I also function against the kernel. Kernel is different. Yeah. Simple.
So
Rarer. Yeah, log VRA V hat invariant, but it's rarer. Right, so that's where I'm working. Thank you.